Hello students. So in the last class we started with line integral, and today we will continue with probably with our last example which we started, and then we switched to surface integral. So in the last class we started with this example where we needed to evaluate this integral along the closed curve given by this curve here and the line from 0 0 to 1 1. So we can actually draw the figure, and the line from 0 0 to 1 1 is a straight line passing through the origin. So this is our line, and the curve is given in this fashion, and they intersect of course at the point 1 1. So if we substitute y equals to x here, then it will be basically x cube minus x square. So from there we can be able to calculate the point of intersection as 0 and 1, and when x is 0 then y is 0, and when x is 1 then y is 1. So these are the 2 points where they intersect. Now that we have the curve and we have the line, so we basically have our closed curve, and now we do the calculation. So how can we do that? So of course here the line integral can be done in 2 steps. So first we do the line integral along this curve, and then we do the line integral along this curve. So let us see. So we have x plus y whole square, x plus y square dx plus x square minus y dy. So we can write this one as line integral along the line AO, x plus y square dx plus x square minus y dy plus line integral along the arc OA, and this will be x plus y square dx plus x square minus y dy, right? Because we have to divide it into 2 segments. Now along the line y equals to x, I can substitute along the line y equals to x, I can substitute y equals to x here, and y equals to x here, and x will vary from basically 0 to 1. So let us do that. So I can do that along the line. So along the line AO, I can do 1. So x is varying from 1 to 0. So we can write it as 1 to 0. I have x plus y square. Is that y square? So y equals to x along this line. So I can substitute y equals to x square dx plus I have x square minus y. So y is again x. So let us substitute that, x square minus x, and dx equals to dy equals to dx. So I write dx here, all right, plus for the arc x is varying from 0 to 1. So I can write again 0 to 1. I have x plus y square. So when I do y square, then it will be x to the power 4 by 3. So I can write x plus x to the power 4 by 3 dx plus x minus y square, I believe. Yes, x square minus y. So x square and minus y will be x to the power 2 by 3. So this will be x square minus x to the power 2 by 3. Then here dx. And if we integrate the whole thing, so of course integrating would not be that much difficult, because we basically have an algebraic expression, and I'm pretty sure you all can be able to do that. So we'll avoid that doing that here. So if you do the whole calculation, then you'll ultimately obtain 1 by 84. So this is the required answer. Now this example is in particular interesting because here we had to divide the line integrals into two segments basically. So yeah, first we integrated with respect to this line segment, and then we integrated with respect to this arc here, and the sum will actually give you the integral along that whole closed curve, because they are closed, and that's basically our answer is. So this is how we calculate the line integral. So you always have to identify the curve. In case of line integral, you always have to identify the curve and its parametric representation, or the range for the variable x and y, and based on that we either in this case, in the previous example, we didn't have to put the parametric representation, we managed with x and y representation itself. But if you need to put the parametric representation of the curve, we can also do that. We saw those one or two examples like that, and then you integrate with respect to the parameter t, and use the limits of the parameter t. Otherwise, you can also integrate with respect to x and y and divide the given closed curve. If it is composed of two different segments, then you divide the closed curve into two segments, and then you do the integration like the previous example. So the line integrals are not that difficult, and they are also very interesting. So I'm hoping you would how to say, find it interesting when you practice it by your own. And we will also try to include some formulas or assignments, basically, not formulas, assignments in your assignment sheet for you to practice. All right. So more or less most of the examples are of similar type, so we'll skip these examples. And now I'm in my lecture note. Now I'm going to start with our next topic, which is basically surface integral. And in surface integral, here we'll evaluate some surface integral, obviously, and also we will evaluate some volume integrals. In our vector calculus part, we'll do the same thing actually. So in vector calculus part also we will evaluate surface and volume integral, and of course those will be motivated from the vector calculus point of view. So there we will see Gauss divergence theorem, Stokes theorem, Green's theorem, and here we will stick to our traditional surface and volume integrals. If time permits, we might look into the Gauss divergence theorem or Stokes theorem in the integral calculus itself. If not, then we will cover those topics in our vector calculus part, which I'm hoping to start in next one or two lectures after, actually. So let's start with the surface integral. So surface in R3. So a curve or a surface in R3 is a vector valued function whose domain is a subset of R2 and the range is a subset of R3. All right. So if FGH are three real valued functions defined on a domain D subset of R2 such that x equals to f of uv, y equals to g of uv, and z equals to h of uv. So then the set then the set FUV, GUV and HUV, sorry, so there is a comma, HUV is a surface in R3. So all of this, so this will give the point X, this will give the point Y, and this will give the point Z. So the collection of all these points will actually represent a surface in R3, and we will actually do the integration on these surfaces. So let's see how we can do that. And in our case, whatever surface we work with, they are always smooth. So that means all of them will have a continuous partial derivatives. With respect to these variables actually. So now, how can we calculate the surface area of a surface area? So the formula is the area of a smooth surface. The area of a smooth surface so that means they have continuous partial derivatives. X equals to FUV, Y equals to GUV, and Z equals to HUV. HUV is defined as the double integral integral over the domain D for UV, and here we will have square root of the Jacobian of del YZ del UV whole square plus del ZX by del UV plus del XY by del UV whole square du dV. If we simplify these formulas, so if we consider a surface, so if we, let's say, so these are basically the Jacobians, but we have to simplify this formula. Now if I write, so if we write the surface as Z equals to fxy, so if this is the given surface, or we can write x equals to u, y equals to v, and then z is our f of uv. So again, x is equals to some huv, y equals to some guv, and z is our fuv. Then in that case, we can calculate these individual Jacobians. So calculating these individual Jacobians will not be difficult. We have already done the calculation. So this, for example, is del y del z, del y del u, del y del v, then del z del u, del z del v, and then we do the calculation of that determinant. That will give us the first Jacobian. Then similarly the second Jacobian, similarly the third Jacobian. So if we do all those calculation, then we'll basically obtain, let's say, if we will basically obtain the surface integral, which I am going to write as IS is equals to integral over the domain D square root dx 1 plus del z del x. It's a formula basically, del z del y, where D is the projection of the surface, on xy plane, right? And if I do the projection on let's say zx plane, so then in that case this will be del z del x. So this is so this is the projection on del z plane. Now if the given surface is, if the surface is x equals to say gyz, then again I can substitute y equals to u and z equals to, then we can then I can substitute y equals to u, z equals to v, and then it will be x u v, and therefore the required form will be del x del z, and then here it will be del x del z, and then del x del y whole square dx dy dz, where d is the projection on yz plane. And similarly, if the surface is let's say x equals y equals to h zx, then is integral over the domain D 1 plus del y del x plus del y del z dz dx, where D is the projection on zx plane. So here it also depends on in what form you are given the equation. So if you have the given surface as x equals to fyz, then we basically opt so if the given formula is z equals to fxy, then we basically obtain the first formula, and then we use the first formula. Actually, if we are given the equation of the curve as x equals to zyz, then in that case we'll use the second formula, and if it is given y equals to hzx, then we use the third formula. So it also depends on the fact that in which form you are given the surface, and based on that we can use either one of these formulas. So I think it was a little bit abstract, so let's start with the first example. So example 1, find the surface area. Let us find the surface area of a curve which is, or of a surface which is already known to us. So find the surface area of the surface x square plus y square plus z square equals to a square. Now just looking at this curve, at this surface, we can easily say what kind of surface it is. It's our sphere. All right. So we know that, so instead of surface I can write now sphere, now that we all know. Now we know that surface area of a sphere is 4 pi a square. So let's see whether we can be able to obtain using these integral calculus formula or not. So let us start. So we have x square plus y square plus z square equals to a square. So from here I can be able to write z equals to a square minus x square minus y square, right? I'm not taking the negative value, so let's take only the positive value of z, right? So this is basically my fxy, isn't it? And now if I have the formula in terms of z equals to fxy, then we can be able to obtain the first formula for the surface integral. So for the first formula I need to calculate, where is that, del z del x and del z del y. So let us calculate del z del x. So this will be minus of 1 by square root of a square minus x square minus y square, and then this is minus 2x. So this is basically 2x, and there is a 2 here, so 2 will get cancelled. So this is basically minus of square root of a square minus x square minus y square. Similarly, I can calculate del z del y equals to minus of 2y 2 times square root of a square minus x square minus y square. So this is minus of y a square minus x square minus y square, right? So now based on this formula, I can be able to calculate 1 plus del z del x whole square del z del y whole square. So this is basically 1 plus x square by a square minus x square minus y square, 1 plus y square by a square minus x square minus y square. So if I take this, if I calculate this, then this will be a square by a square minus x square minus y square. So now the surface area, of the sphere is twice the surface area of the upper half, right? Upper half of the sphere. Upper half of the sphere, right? And further, the projection of the sphere, on xy plane is right. So we have taken the upper half because the surface area of the whole sphere would be just the double of the surface area of the upper half, and if we do the projection on xy plane, then it will basically be a circle. So initially it is a upper half of this sphere, but once we do the projection, then in that case it's basically a circle, which is given by this equation. So the radius will remain same. It's not like if we do the projection, then the radius would change. So the radius would still remain same, and this is the equation of our circle. Now our required surface area will be 2 times d is the r is the projection. So let's write r 1 plus del z del x whole square plus del z del y whole square dx dy. So this is basically 2 times integral from 0 integral over the region r square root, that means this is a, and then this one will be square root of a square minus x square minus y square dx dy. Now this is just our plain integral calculus for the function of 2 variable. This we have already done. So this type of calculation of integral for the function of 2 variable we have already done. So here we basically take help of the how to say polar coordinates actually. So let's substitute putting x equals to r cos theta and y equals to r sin theta, where 0 lesser equal to r lesser equal to a and 0 lesser equal to theta lesser equal to 2 pi. Then this surface integral is would reduce to r running from 0 to a, theta running from 0 to 2 pi. I have a divided by I will have a square minus r square cos square theta minus r square sin square theta, and then Jacobian times r Jacobian times dr d theta. So this will be integral r running from 0 to a, theta running from 0 to 2 pi, a divided by a square minus r square, because we take r square common and it will reduce to cos square theta plus sin square theta. Jacobian of this will be r dr d theta. We have already seen it many times, how we can calculate the Jacobian for this transformation, and therefore we will end up with a times, so of course there is a 2 here, so 2a times r running from 0 to a, theta running from 0 to 2 pi, r dr d theta square root of a square minus r square. So now we separate theta and r because they are not mixed up together. So 2a integral theta running from 0 to 2 pi d theta integral r running from 0 to a, r dr by a square minus r square. Now I substitute a square minus r square equals to z, and then in that case we will have 2r dr equals to some dz, and that can be handled very easily. So calculating this integral would not be difficult. So this will be 2a times 2 pi, and this integral would be minus of a square minus r square, where r is running from 0 to a. So this is basically 4a pi, and when we substitute r equals to a, so this will be 0 plus a, so that means 4 pi a square. So this is the required surface area of this sphere. So where is that problem? Yeah, so calculating the surface area of this sphere, we tried to express the function z, we tried to express the variable z as a function of x and y. So now we are in that z equals to fxy form. So for that we need del z del x and del z del y. So we substituted the value here, and then that is our the square, and then in the formula also we need to take the projection. So before doing the projection, we first need to find out the surface area. What kind of concept do we need to use? So since it is a sphere, the surface area of the whole sphere would be twice the surface area of the upper half. So that's what we have done, and r is the projection. So when we take the projection of the upper half on xy plane, it will be a circle with similar radius. So that's what we have written, and then we are just using this conversion into a polar coordinate system. So this is x equals to r cos theta, r sin theta, where r is between 0 to a, theta is between 0 to 2 pi, and then we just substitute the value, do some simple calculation, and that will give us the required integral as 4 pi a square. So here in this example, we saw that how we can calculate the surface area, and the calculation does match with our traditional concept of surface area of a sphere. So we'll definitely work out one or two more examples on calculating the surface area of a surface. We'll probably see some examples where we have two intersecting surfaces and how we can calculate the surface area. We'll do all those things in our next class, and then we'll switch to volume integral. So I thank you for your attention, and I'll see you in the next class.